Welcome to our video on light dispersion. Today, we'll explore what happens when light passes through different materials and why we see beautiful rainbows in nature. Let's begin by understanding what light actually is. Light is a form of electromagnetic radiation that travels in waves. These waves have different wavelengths, which our eyes perceive as different colors. The visible spectrum ranges from red light, which has the longest wavelength, to violet light, which has the shortest wavelength. When all these colors combine, we see what we call white light. Before we can understand dispersion, we need to understand refraction. Refraction is the bending of light when it passes from one medium to another. When light travels from air into a denser material like water or glass, it slows down and bends. This relationship is governed by Snell's law, which states that n1 times sine of theta 1 equals n2 times sine of theta 2, where n represents the index of refraction of each medium, and theta represents the angle of the light ray. Now, what is dispersion? Dispersion is the phenomenon where the index of refraction of a material depends on the wavelength or color of light. For most transparent materials like glass, the index of refraction is higher for shorter wavelengths, blue/violet light, than for longer wavelengths, red light. This means that when white light passes through a prism, each color bends by a different amount, separating into a beautiful spectrum. Let's see exactly how a prism disperses light. Step 1. White light, which contains all visible wavelengths, enters the prism at an angle. Step 2. As the light enters the prism, each color refracts by a different amount. Blue and violet light bend more than red light because they have a higher index of refraction. Step 3. Inside the prism, the colors continue to separate as they travel at different speeds. Step 4. When the light exits the prism, it refracts again, spreading the colors even further. Step 5. The result is a beautiful rainbow spectrum, with red on one end and violet on the other. Let's look at the mathematical description of dispersion. The index of refraction as a function of wavelength is often written as n of lambda. For many materials, we can describe this relationship using Cauchy's equation. N of lambda equals a plus b over lambda squared plus c over lambda to the fourth power, where a, b, and c are constants specific to the material. The angular separation between colors increases with the difference in the index of refraction for those wavelengths. This is why we see such a clear separation in a prism. Dispersion isn't just a laboratory phenomenon. The most beautiful natural example is the rainbow. Rainbows form when sunlight enters water droplets in the air, undergoes both refraction and reflection, and emerges dispersed into its component colors. Dispersion is also important in fiber optic communications. Different wavelengths of light travel at different speeds in optical fibers, which can cause signal distortion over long distances. Engineers must account for this when designing communication systems. Even our eyeglasses make use of dispersion. Special lenses with low dispersion are used to prevent color fringing at the edges of objects, giving us clearer vision. To summarize what we've learned about dispersion: 1. Dispersion occurs because the index of refraction depends on the wavelength of light. 2. Shorter wavelengths, blue/violet, bend more than longer wavelengths, red, in most materials. 3. This phenomenon explains rainbows and is used in many optical devices. 4. Understanding dispersion is crucial for designing optical systems, from cameras to telescopes. Thank you for watching this video on light dispersion. Next time you see a rainbow or look through a prism, you'll understand the beautiful physics behind what you're seeing.